second plenary session of the Congress. Before I introduce the keynote speaker for this session, I have a few quick messages. The first is a message from the local organizing committee and the associations. It's as follows. Today, during lunch, there are several things happening. First of all, there's a poster session in Handels in room C34, to which you are very welcome. The three associations also have open meetings for their members. No signing up for these meetings is required, and you will find lunch boxes by the rooms, so there is no need to bring lunch. You can find the location for the meetings in the detailed schedule, but note that the American ERE lunch takes place in Haga and not in Handels. And you will find the entrance a bit further down the street from the registration entrance. Look for crew members and flag, and they will guide you. The second message is a reminder from the organizing committee that you can use the Congress app to find and indeed post information about formal and informal events related to the Congress, including the Congress dinner, which is tonight. Buses are departing from 6:15 p.m. All right, so with that said, it's a great pleasure and a great honor to introduce this morning's keynote speaker, Professor David Hendry. David Hendry is the director of the program in economic modeling at the Institute for New Economic Thinking at the Oxford Martin School, a co-director of the Climate Econometrics project and network, professor of economics at Oxford University, and a fellow of Nuffield College, Oxford. He was previously a professor of econometrics at the LSE. He was the chair of the economics department in Oxford between 2001 and 2007, and he has held visiting appointments at Yale, University of California, and Duke. He has published more than 200 papers and 25 books, and his works have been cited more than 40,000 times, according to Google Scholar. He is an honorary vice president and a past president of the Royal Economic Society. He received a Lifetime Achievement Award from the ESRC in the UK in 2014. He has been awarded 8 honorary doctorates, and he was knighted in 2009 for services to social science. So it's a great pleasure to hand over to Professor David Hendry, whose presentation is entitled Climate Econometrics. David will speak for approximately 45 to 50 minutes, leaving some time for questions before we break for lunch. David, the floor is yours.
A topic that had a title that immediately appealed to everybody. I know from teaching econometrics in Oxford that it can be challenging to get people really interested in the arcane details. Thank you, Mons, for a very kind introduction. I guess the audience is immensely diverse. There'll only be 2 slides on econometrics. I want you to concentrate on them when they come, but otherwise it's almost all about applications. Now, why are we doing econometrics of climate? Well, the approach we adopt in macroeconomics has got to deal with various non-stationarities, and these are reflected in climate because they're both connected by human behavior. So wide-sense non-stationarity means there's stochastic trends that are driving the system in an evolutionary way, and there are sudden shifts that cause changes that are too big to be picked up by the variables in any model. And to deal with that, we've invented methods that we call saturation techniques, indicator saturation techniques, that deal with outliers, distribution shifts, changes, volcanic eruptions. I'll discuss them all. We have to have model selection procedures that handle more variables than observations. At first sight, when you pick up a standard econometrics textbook, they say, oh, you've got to have as few variables as you can possibly get off with. At the end, yes, but not at the beginning. At the beginning, you need to put in everything that might matter. including your theory and all the associated variables, and we always include lots of indicators for things we don't know about. Now, we can retain theory models. I'm not going to discuss that today, but when we do so, the distribution of your parameter estimates is completely unaffected by any amount of model selection, something that tends to astonish people. Even if you start off with 1,000 variables for 100 observations and you've 10 theory variables, the distribution of your estimates will be unaffected by selection. And finally, we have tests for evaluating our models. I'll try to explain why all this works, why you should be adopting it in all areas of environmental and climate applications, because we don't know what has happened. The idea that we fully understand the system is just not on. We work closely with dendrochronologists, volcanologists, geophysicists, climatologists, oceanographers in order to get the outside physical sciences involved when we're analyzing any of these problems. And the methods, although they're mainly time series today, are equally applicable to cross-sections, panels, and so on. They can handle nonlinear models, but that's not part of today's discussion. The good news will come from the first of the sections. UK CO2 emissions analysed annually from 1860 to 2015. The bad news will come, as one of the previous speakers said, from global CO2 concentrations monthly. We look at the impacts of volcanic eruptions and temperature reconstructions, partly because we want a baseline temperature for the Earth that's independent of the Industrial Revolution, which actually started in 1760, not 1860, as some of the data do. We're interested in looking at the costs of extreme events, so I'll look at misforecasting hurricanes, I'll look at local and global climate changes, but I won't talk about our work in attitudes and beliefs and sea level rises and the damages they'll do to coastal cities. So the Industrial Revolution started in the UK in the mid-18th century, and the startling consequences are almost everywhere. There's huge increases in real incomes over what there would have been without an Industrial Revolution, 7 to 10-fold in very many countries. And our world in data has got lots of the positive news about what's followed for humanity in terms of longevity, reduction in poverty, and taming many deadly diseases. But the unintended consequence has been a massive increase in CO2 emissions. The panel A to your left shows what's happened over the ice ages for the last 800,000 years, and then we pick up from Keeling's Mauna Loa data of CO2 from flask measurements in about 1950, and they're way outside the range, about 100 parts per million higher than they were previously. Now, why are we interested in CO2? It's just a gas. In fact, there's a shortage of CO2 in Britain at the moment, and Coca-Cola stopped bottling things, chickens aren't being put to sleep before they're being killed, etc. It's a real problem. CO2 is just a gas. Well, Eunice Foote in 1856 showed that if you put out a flask of air, a flask of water vapor, and a flask of CO2 in the sun, and then you took them in 2 hours later, a long time after that, the only one that was warm was the CO2 flask. CO2 is a greenhouse gas. So is water vapor, but not to such an extent. Of course, she couldn't get it published just because she was a woman, but at least her work was reported by one of her male colleagues. Since then, CO2, things have changed a bit, I'm glad to see. Still some way to go. Since then, CO2 has been accelerating. That was noted again by a speaker. It's not coming down aggregately. Temperatures are rising, most in the Arctic and Antarctic, relatively speaking, but globally, and certainly in the oceans, down to 700 meters, and more than twice as much down to 2,000 meters. So, how do we pick models to analyze data that look so non-stationary? And the answer is, every decision you make about how you formulate your theory, how you implement it, its evidential base, its empirical specification, and its evaluation, they all involve selection. I meet very few people who realize they're selecting a theory, they're selecting the data, they're selecting how they study it, they're selecting how they evaluate it. Everything involves selection. It's not the refuge of scoundrels, it's an essential component of how you do any empirical work. And I want to drive that message home, as model selection's got a bad reputation in economics, totally stupidly, by people who did appallingly bad Monte Carlo studies of really awful model selection methods, and like taking a cigarette lighter out of a car and throwing it away and saying, therefore, the car is useless. That's what model selection theory has come in for. But absent omniscience, for empirical modeling, selection is inevitable, unavoidable, and ubiquitous, but often unreported. The issue is not whether to select, but how to select. We've got to discover what's going on out there. It's not known to us what actually matters empirically, while retaining all the theory insights. It's not data mining, that goes on in some areas, but we're actually keeping all the theory insights. If you've got any theory insight, it's retained. And the rest we then try to see, is that theory complete, correct, and immutable? Because I guarantee it is not. There's never been an economic theory that's complete. There's never been one that's immutable. Just think about what economists were writing in the 1850s and imagine that you had to impose that today when you did any empirical research. Our software is Autometrics, developed by Jürgen Durnik and myself. So the next two slides, please concentrate. These are the only two serious ones on econometrics. Don't go to sleep now, despite your morning break. So, consider the simplest possible linear, perfectly orthogonal regression model, where there are n variables, and I'm going to take n at 1,000. Now, not many of you will have fitted models of 1,000 variables, but it's perfectly feasible. So, the betas are constant, the z's are independent of the other, the z's are all mutually orthogonal, and you've got 10,000 observations to do this from. You're in geophysics, perhaps the atmosphere, looking at the troposphere or something like that. Okay. What do you do? Well, let's fit the model. With 10,000 observations, it's easy to fit 1,000 variables. And compute the t-squared statistics for every parameter, squaring just to get rid of signs. We don't want to be bothered by that. And rank them. Now, if you've ever done computer programming, ranking takes an enormous amount of effort. Right? Now, here it's trivial because you can see the numbers and just order them. But if you couldn't and you had to rank them, it would look like a lot is going on in the program. And I'll come back to that. We're going to retain the variables of the largest t-squared values, called tau squared once they're ordered, up to number r. And then we're going to throw away all the others. And you can choose your critical value, 5% critical value, 1%, 0.01%. We use a lot of different critical values depending on n. For 1,000, we use a 1 in 1,000 critical value, and I'll discuss that in a moment. Only one decision is needed to pick the model. One decision. There's no repeated testing. You never look at goodness of fit. If your program does repeated testing and looks at goodness of fit, it will get it wrong. You've got to do it with one cut, right? That doesn't mean it has to be orthogonal. I'll explain that shortly. But there's none of the distortions you get from model selection is necessary. The average false null retention ratio can be kept at 1, even for 1,000 variables by using a 1 in 1,000 significance level. Now, the approach doesn't require non-orthogonality. The explanation, to make it obvious to you, I hope, does, because once you've cut, there's no change in the parameter estimates for the ones you keep over the ones that you got for the 1,000 variables. They stay exactly the same. When they aren't orthogonal, the model's got to search to get the order. And that's what takes the time. There's a lot of searching, because when they're non-orthogonal, depending what's in, you'll get different answers. But it can still rank the tau squareds pretty accurately, and then you do one cut once you've got the ranking. It can deal with n bigger than t. It just takes an awful lot longer. It's got many, many more models. If n is 1,000, 2 to the 1,000 is almost the number of atoms in the galaxy. So there's a lot of models to look across. But we look across large numbers of them. Not all of them. We've got lots of shortcuts that I won't talk about today. But once you've got the ordering of the tau squareds, one cut, you're all over. There's no selection. You've done it. You have your model. Why 1 in 1,000? Well, the critical values that you need to avoid picking up garbage have an impact in whether or not you keep relevant variables, but not much of an impact. Going to 1 in 1,000 for 1,000 variables raises the critical value to 3.35. Now, if you've got 10,000 observations, a critical value of 3.35 actually isn't very significant at all. It probably contributes 0.01 to your R squared. So if you don't keep a variable between 2 and 3.35, it's not going to matter terribly much. But the trade-off is not retaining relevant variables with these t-values. And those are not terribly relevant variables. And in any case, you'll keep all your theory variables independently of the significance. So the only thing you're missing are things you didn't know mattered, and you now still don't know they don't know matter. But you might learn later from other discovery procedures. So the main application of this at very tight alpha, the 1 in 1,000, is in our indicator saturation approaches. So this, I'm afraid, is a rival university called Lund just down the road, and that's the chapel there, those of you who have local connections. But this is the key reference, empirical model discovery and theory evaluation, how to keep all your theory variables unaltered by selection, but discover what's actually going on out there. Now, indicator saturation is a wide class of methods, and the methods are designed for particular problems. The first one I'm going to talk about is designed to pick up outliers and data contamination. Now, when you work in climate and environment, your data is often contaminated. People wrote down the wrong numbers, recorded deliberately misleading ones. So to deal with that, create an indicator for every observation. So if we have 100 observations, it goes 1, and then 99 zeros, 0, 1, 98 zeros, 0, 0, 1. For every observation, we're going to put them all in. Now, of course, if you put them all in simultaneously, you'll get a perfect fit, which will tell you nothing. So we put them in very large blocks, and I'll explain how that works. Because most of you have done this, but didn't know you were doing it. It's like speaking prose. You're doing it all the time. So here's a terribly simple example of 9 observations. 0 will be explained shortly. The ones before 0 are negative, the ones after are positive. It's a simple time series, a mean of 6, and a variance of 1/4. We create 9 indicators. We put in the first 5. Now, putting in 5 indicators is a perfectly standard regression analysis of 9 observations. You then will pick up indicators that deviate from, is this thing got a, no, oops, sorry. I was hoping it might have a little pointer. Nope. Why doesn't Control L work?
Yes.
Oh, it's the other. Nope.
Yeah.
Okay, thanks. Is there a light?
Yes. No, it's not good.
No. Okay. Right. If you look at the data, towards the left, when you put in the first 5 indicators of the 9, you put all the observations to their 0 value. And indicators that will be significant, they deviate from what's happening in the second half, and that doesn't happen. When you put in the next 4, it compares what's happening in the first half, given the mean and variance there, to see if any of them are significant in the second half, and again, that's just not the case. Yeah. And therefore, although we've put in as many indicators as observations, we've kept none. Well, none were mattering because the data hasn't got any outliers. And the forecasts that you get out are unaffected by having done model selection. What are the provable properties of our approach? Because you might think putting in more variables and observations, you couldn't prove anything. There's a brilliant paper by Søren Johansen from Copenhagen and Bent Nielsen in Oxford, which establishes analytically the properties of doing what we're doing. So we take the same thing, I've written it now in matrix form, y is beta prime z plus epsilon, the betas are constant, the epsilons are orthogonal to the error, but they're not necessarily orthogonal to each other, and the error is well behaved, but that's also not needed, it's just to guarantee the explanation. Then if you do impulse indicator saturation, your estimator after doing it converges to the true parameter value at the usual rate of root t, despite more candidate variables and observations. The limiting distribution is normal, but with a variance that's slightly larger than your usual one, sigma squared x prime x to minus 1, where orthogonality is not required. So the actual limiting distribution can be written down, root t, beta tilde minus beta, tends asymptotically to normal of the correct dimension with a mean of 0, the usual variance covariance matrix with a little capital omega alpha at the end. Now, depending on how you set C of alpha, capital omega alpha is the cost of having done it all. It's a very small cost. It's 1 minus alpha to minus 1. So if alpha is 1 in 1,000, the cost is 1.001 over what you would have got by not trying to find out if you've got outliers, data contamination, or breaks. The cost of doing it is nearly trivial, but the benefits are huge. So let's look at the same data, but now we've got an outlier starting at 0 and hitting at 1, and just for one observation. We again put in our first 5, doesn't find anything. We put in the next 4, it immediately finds a hugely significant indicator corresponding to the outlier, because there's a break of more than 4 standard deviations as here, and it's retained in black, and now it makes a difference. Now the forecast interval you get out of your model is quite a lot smaller than if you hadn't dealt with the outlier, and the forecast value is distinctly higher. It's back at 6, which is the correct mean. Whereas if you don't do it, you get the incorrect mean. It's really important to deal with outliers. Indeed, if you don't, you might get the wrong signs on your theory variables. Now, I know you've all done it. Well, anyone who's ever done recursive estimation has done an inefficient use of impulse indicator saturation. They fitted the model to a small subsample, and that's exactly equivalent to putting in indicators for all the rest of the data. But they don't look at the indicators. They only look at the small subsample. So they're throwing away a lot of information about what's happening. Moving windows, some at the beginning, some at the end as you move through, but again, they don't look at the indicators. Hold back, which is often used in North America to evaluate models, is a silly way of doing it because it's equivalent to IIS over excluded data points. I see people excluding wars. I often see many people claiming their forecasting method is great, and they stop in 2008 because they know if they go any further, it will fall apart. That's again doing IIS, but not looking at the value of the indicators. And if you've ever done a Chow test, you've done impulse indicator saturation on a claimed specific subset of data rather than trying to find where the breaks actually are. So all of these could detect a shift if you knew the rest of the model. But an advantage of IIS is it can find multiple shifts at very different points all over the data without knowing what the model really is that you're working with, selecting that at the same time. Now, we designed these for outliers, but the key thing in economics are actually location shifts, regime shifts where the data suddenly alters. So let's look at what happens if we use step indicators. Same data. This time, I've picked 4 kind of spaced out steps. So the step starts at observation 0, goes down to -3, and then 1, 0 down to -1, and so on. You put in the first 4, doesn't find anything. Put in the second group of 4, doesn't find anything. We get exactly the same forecasts and outcomes as we did with IIS. Now let's have a location shift. Here the location shift is a permanent effect of a downward shift of -1, and the mean goes from 6 to 5. When you put in the first block, it picks up a step shift going from the start and coming down at 1. When you put in the second block, it doesn't find any more. And when you come to forecast, you get very, very different answers. The confidence band, if you don't do this, is enormous, and the forecasts are not very good. They're almost outside the confidence band after doing it. And the confidence band after doing it is back to the 1 that's due to the random error shocks. And the mean is now the correct mean of 5. So you can pick up these. And we've done up to 20 shifts in 100 observations. So you can have very contaminated data and still get it working. That's it, folks. That's econometrics for today. I hope that little lesson has sunk in to some extent. Okay, we're going to apply this now to all these things. UK CO2 emissions, global CO2, volcanic eruptions, hurricane damage, and 1.5 versus 2. So here's the good news. The UK CO2 emissions per capita, despite a 7-fold increase in real income, are below any level since 1860, when we were the workshop of the world. That's how much we've cut them. It's really dramatic. The only other value that's below was the 1926 general strike, which you can see is a big outlier. Now notice the non-stationarity, a big rise, violent behavior in the interwar period, a rise and then a complete collapse. Do not use methods that assume stationarity when analyzing climate data. Please, if that's the only message you take it away, right? They don't work and can't work. The data are not stationary. They're hugely varying. This is amongst the most extreme, but just imagine other European countries, Germany with the 2 world wars, France, etc., etc. They're all hugely varying. The Great Depression in the US, it's not stationary data. Nor are the fossil fuel consumption. Coal rose dramatically to 1920, oscillated violently, rose again to 1960, but it actually started leaving the British system as early as 1960, and it's fallen very dramatically. This data stopped in 2015, but it's almost out of the British system now. We almost use no coal domestically. Oil rose dramatically because of Churchill's decision to use it in British warships in the wars, and then it starts falling after the oil crisis. Prices still matter, folks. Gas rose dramatically. I'll explain what we find for that. And then renewables are coming up like a storm. Now the cheapest form of energy in Britain is onshore windmills, wind turbines. That's the cheapest. It should drive everything else out of the system so long as there's wind. And if you've ever been to Britain, wind? Yeah, we have a bit of that. CO2 emissions are strongly affected by the existing capital stock. Britain and the US, actually, the ratio of CO2 emissions to capital stock since the 1860s has fallen by 92%. We really have improved efficiency, but we've got a long way to go. Stranded assets are problematic as legislation might lower CO2 targets. Stranded assets for a house in a floodplain or diesel cars after they're banned. Here's another implication of the non-stationarity. CO2 in the vertical axis, coal in the horizontal. CO2 rises with coal to the 1960s, continues up with oil to the 1970s, and then comes back down. These are the location shifts. This is the distribution of CO2 emissions in total in the UK in the 19th century. That's up to the Second World War. That's after the war till 1980, and then it jumps back later. The distribution is shifting all over the place. If you don't deal with distributional shifts, you won't get sensible models out. So to capture this, we use coal, oil, capital stock, and GDP, dynamics for adjustments to technology, legislation, fuel prices, impulse indicators for outliers like the strike action in 26, and step indicators for major permanent shifts. Now remember, we've now got about 330 variables for 150 data points, but that doesn't matter. It doesn't very little effect on what's going on. Right. The model selection proceeds in 4 stages. We hold all the theory variables unselected and select across impulse and step indicators at 1 in 1,000. We then check the model as well specified. We then select over the economic variables, as not all of them may matter. We then derive the co-integrating relationship, and then we evaluate and forecast from the model. Now, when we find large indicators, particularly step indicators, the interesting question is, do they coincide with anything in the data? It's not that we came along and said, oh, 1925 saw the Act of Parliament creating the UK's nationwide electricity grid. We found an indicator in 1925, then we looked to see what does that correspond to. And indeed, it hugely increased the efficiency of Britain's electricity usage. 69 saw the start of conversion from coal gas to natural gas, and 2010 follows the UK's Climate Change Act of 2008 and the EU's Renewable Directive of 2009. Now, it's crucial we do not impose that policy had an effect. There may be other things going on when you do that. What we do is we see what the data tell us about shifts, and then we see if they have an effect. We found one for 1991. In fact, emissions are a bit higher than the model explains, and I still am not sure why, but it picks up that. When we select over the regressors, only eliminate G, and then we check for co-integration, get very strong co-integration between emissions and these variables. Coal and oil have roughly the weights of their emissions per unit BTU, capital 0.2, and notice GDP negative. Right? Now you might think, gosh, that's the wrong sign. I've fitted environmental Kuznets curves and it's positive. That's because you're doing the wrong thing. You should be fitting general models and finding out what actually matters. This is reflecting the shift to Britain becoming a service economy. And as it became a service economy, CO2 fell relative to capital, oil, and coal. Right? Because we haven't got other things in the model. And then we pick up that up to 1925 it was higher, 69 it was lower, and 91 it was lower. The co-integrating relation actually describes the data by itself, but we then transform to a difference and equilibrium correction model, and this is how well it describes the data. Picks the bold show the big shifts, 25, 69, 91, and 2010. The parentheses show the outliers that are picked up, only a few of them, and they're very, very big outliers, which heavily distort if you don't do it. So what are the benefits? Well, we can get conditional one-step forecasts each year, and it suggests that the Climate Change Act hasn't operated as quickly as the model thinks it should have done for either the differences in the top graph or the levels in the bottom graph. Robust methods, which we also talk about when we talk about forecasting, actually do much better than conventional methods, and I can commend, if you're forecasting, to go and read about our robust methods. Unconditional system forecasts up to 4 years ahead. If you do the model with the vector autoregression with SIS, you get much smaller root mean squared errors for the one step and dramatically smaller for the multi-step, which are the interesting ones. And if you haven't done SIS, your forecasts are badly wrong by the end of the period. Is the UK achieving its targets? Well, the blue line on the left graph shows the targets, the red line shows what happens. If we apply step indicator saturation, which can work perfectly well with only 10 observations, we find a massive downward shift starting in 2012 and dropping way down. So we actually can strongly reject the hypothesis that emissions equals targets, rejecting the negative side, and this can be used to check whether NDCs from Paris are working. Will it achieve its targets by 2050 of an 80% reduction? Well, it needs an enormous reduction in oil, coal, gas, and agriculture, construction, and waste emissions. But it could get there. It's not impossible to get down. The trouble is, 120 megatons per annum is still far too high if we're going to get net zero. So it's an unambitious target, but still going to be quite difficult to achieve. What about global concentrations? This is work with Felix Pretis, who's here talking this afternoon in a climate econometric session, which some of the other talks will come out. And we've put in 492 variables for 246 monthly observations, constant trend, seasonal dummies, impulse indicators. The program estimated 571 models, selected 14 variables at 1%, but did not keep any deterministic terms whatever. It attributed everything to human or natural behavior, and the only things that accumulate the concentrations to go through the actual emissions are human activity. It just confirms what we know from isotope analysis. Southern Oscillation Index is going up, vegetation uptake is going down, but they're tiny scales compared to the trend. What about the impacts of volcanic eruptions and temperatures? Now here we're going to design indicators to match what happens when you get a volcanic eruption. When you get a volcanic eruption, and there's several possible ones here that the dendrological temperature record might be distorted by, and they create outliers in that record because they throw up emissions that block solar radiation, sometimes dramatically like El Chicong, sometimes a bit like Pinatubo, but the shape of that response is relatively standard. As the eruption comes out and all the stuff goes up into the atmosphere, stratosphere, or troposphere, whatever, depending how violent it is, there's an immediate drop in temperature that year. And then there's a recovery. Think of the Greek letter nu, come down and then go up slowly. So we can design an indicator to match that. And these are the shapes of the indicators, looking like Greek letter nus. Graph A in the top right is exactly like I've shown you for step indicators, but the indicator is designed appropriately for the problem that it's being applied to. And when we apply it to volcanic eruptions, we pick up almost all the volcanoes that have been recorded historically, and we can correct the temperature record for the impact of those volcanoes on what has been happening. It also helps in forecasting. Those of you who ever unfortunately use equilibrium correction models in the belief that they might be useful for forecasting need to know that they're absolutely useless for forecasting. They go in exactly the wrong direction. And I've kept in the AR1 forecast here to show you, because they're trying to equilibrium correct. And they think the data's falling, so you're not doing enough, so you better do more. And of course, it's completely the wrong direction and gives you appalling forecasts. Whereas if we include the break indicator, it's not exact, but it's quite close. That's the orange curve. It's vanished, or it's still there? It's vanished from my screen. Okay. Hurricane damage, extreme events. We're going to get lots more of them. What can we say about them? Well, hurricanes have caused 5 of the 10 costliest weather and climate disasters in the US in the last century, this century. I mean, they're really enormous. Climate change can alter the location, frequency, and intensity of storms. And one of the questions we're interested in is, does forecast uncertainty about the location of the hurricane affect the damages that it ends up causing, in addition to all the natural things that will cause damage? So we include everything. income, population, housing use and historical frequency, wind speed, pressure, max storm surge, max rainfall, cyclone, energy, soil moisture, air temperature, and forecast uncertainty, plus 35 other variables. Then we ask the same program to do selection, and what it finds is that income, housing units, the three major pressure, surge, and max rainfall variables, and forecast uncertainty help account for the damages. And when we then compute, this model's 2 years old, so it hasn't been, the data for Harvey have not been included in the model estimates. When we use it to forecast what the official damages from Harvey will be, just using the program by itself, it's second closest, Lasso's way off. Using the GETS, general to specific, with IIS, it's very, very close to official estimates, and previous models are even further out. What about the impacts of 1.5 versus 2 that will come up again at our session this afternoon? IIS helps mitigate the non-linearity. It flattens it out a bit. And when you apply it to data, I can see I'm running out of time, which is why I'm kind of going fast, but you can hear about this afternoon, so I'm not so worried. Then 1.5 versus 2 does have quite a big impact. It's really worthwhile aiming for 1.5. It's probably just about possible. There's only one country that benefits, and that's fairly marginal. And I'm sure, since Felix Pretis is one of the co-authors and he's about to move to Canada, that's why he's made sure it shows up in green. So what conclusions do I draw? On econometric modeling, despite many, many more candidate variables and observations, the econometric approach has seen many successful applications. I've only given you a subset of the ones that we've published over the years. It's essential to take account of the non-stationary nature of time series, both the stochastic trends that lead to co-integration and distributional shifts that cause very bad forecasts if you don't allow for them. The tools have been effective in climate applications, explaining UK CO2 emissions, anthropogenic origins of increased atmospheric CO2 levels, the impact of volcanic eruptions on temperature, more accurate hurricane forecasts, help mitigate damages, and we can estimate GNP costs of temperature changes. The software is available as Artometrics in Oxmetrics 8, recently released by Jürgen Durgan and myself, and currently in the Timberlake website, and as GETS in R if you're an R user. It's available in the CRAN depository. UK climate policy has been effective. I heard someone moaning about politicians. If you know the politicians, I happen to know Greg Clark quite well, and you know the people who are going to bring it about, and they really understand the damages that are going to come about, you can get effective climate policy. The Climate Change Act has really raised the cost of coal, subsidized the cost of renewals, and caused a big switch, and that switch is now almost ineluctable. It will continue, I think, unchanged. Large reductions in CO2 emissions haven't shown up as an aggregate cost. Local losses haven't been addressed, and that really annoys me. The people who've suffered throughout history when new technologies come in have been left to suffer, even in such a rich country as mine, in the 21st century. I think that's a disgrace, and politicians should be thoroughly ashamed of themselves, not trying to do something with the areas where mining and shipbuilding and steelmaking have been decimated by the changes, which benefit us and the world. I completely agree that Britain should be investing heavily in these new technologies because that's the future. It's a benefit to come out of trying to tackle climate change rather than looking at the costs. Stranded assets will be a big problem, and I'm glad to say 2 of the biggest oil companies in Britain are taking that very seriously and beginning to move towards trying to introduce more renewables into their portfolios. At a global level, 1.5 versus 2 is still possibly achievable. We can correct temperature records to a good baseline, not from 1860 to 1880, which I do not think is a good baseline for IPCC, but much further back when it was not being disturbed. We can model and forecast damages from hurricanes. And Luke Jackson, who's also talking sea level rise by the end of the century, really worrying. 10% of the Earth's population live in cities close enough to the oceans that they will be in serious trouble by 2100. Not going to bother me, but it might bother some of the children that would like to be better educated children. Major CO2 reduction efforts are still needed to even approach a net zero emissions target. And thank you very much for listening. Richard.
Well, thank you very much, David. That was extremely interesting. So we have about 15 minutes for questions, and I think it's rational to do them sort of section by section. So why don't we start up at the top, if anybody has a question there. We, of course, encourage people to be brief and to the point. Is there a question over here, maybe? Just to wait.
My question, is it understand? Oh, yeah. My question is, is there any cost of IIS? So is there any cost of leaving out the outliers? I'm thinking about a model on pricing in finance, and so there you typically don't want to leave out the outliers, the very steep drops in prices to fit your risk model, because the model would be not enough prudent. So more generally, can you do something wrong by just adding a dummy variable for your outlying observation?
I think you're misinterpreting what impulse indicator saturation is doing. It's not taking out outlying observations. It's taking out observations that are outlying relative to everything else you've already got in the model. Right? That's what it's doing. So if you've got anything in your model that's explaining the risk, that drop, or whatever, it will not affect it at all. It might be a nonlinear effect. It will not affect it at all. It will only take it out if nothing else is taking it out, in which case it's distortionary. Now, it wouldn't be distortionary for a variance, because you might want to calibrate the risk against a world with lots of outliers. It might be a T3 distribution and outliers are appearing. But once you've calculated, say you're using GARCH or stochastic volatility for calculating that risk, if you now don't take out steps in that, you'll find a unit root. That unit root to be completely spurious, if in fact it's due to location shifts in the unconditional volatility that you're not modeling because you're assuming that's constant. So even in cases like that, we find it's hugely advantageous to use all these methods.
Next question.
Okay, there's one down here.
We have a couple down here, so we go downstairs. Hang on.
Richard Carson. David, it seems like one of the things that would fall out of this is that there's a huge gain to increasing the length and sort of frequency of a lot of these time series in terms of what you're able to tell. Going from annual data to quarterly data to monthly data and going back to the 1700s. And this is a question that a lot of this is physical science data. And this is really something that I think economists could help quantify the value of reconstructing a lot of these series.
Yes, thanks, Richard. The UK has invested a vast amount in a project run by Steve Bradbury to calculate all the relevant economic variables from 1320 to today. And this was done to answer a number of really key questions, both about climate change, how much was agricultural output changing, conditional on the existing technology, but it's also to try and explain where on earth did Britain get the money for the Industrial Revolution. It's one thing to invent governors and whatever for steam engines. It's quite another to have the investment available to actually implement it. And what their study has shown is indeed that the average will left between 1320 and 1760 doubled. And it doubled probably, I have to say, because of the Protestant Revolution, because the number of holidays dropped from 120 to 40. And so people just worked longer, they didn't spend all their money, they built it up, they left it to their kids, who left it to their kids, and gradually you got enough money to fund the Industrial Revolution. So this data is utterly invaluable. The trouble for me, having tried to analyze the agricultural output, is agricultural output depends on greatly within year variation. Did all the rain come in January, or did it all come in September when they're harvesting? Did it rain equally throughout the year? All we've got is a rainfall figure for the year, or approximations to it from various records. We don't actually have good enough data within year. Yeah, higher frequency, we did better in the monthly than the annual. We don't have monthly data from 1860s. It's been one of my pet projects to keep prompting the economic historians and the ES, the Economic and Social Research Council, please invest in better, longer, more high-frequency data. Finance has got second-by-second data, even tick-by-tick data, and they've made quite a lot of semi-progress in trying to understand finance. I think we could do much better if we got a lot better data. There was another question slightly further back. Yes.
Thank you. Alexander Golub. And I have a technical question to you. What is the role of normal distribution? Is it assumption or it is a result? Because talking about standard deviations, like for standard deviation for normal distribution in one story, for student distribution is completely different. So can you comment on that, please?
Okay, it's a result. The whole point of using impulse indicator saturation is if you started with a T distribution, you'd get lots of outliers. Those outliers are perfectly natural. They are draws from a T of 3. They will happen. But if you look at the distribution of the parameter estimates and the correct standard errors for those parameter estimates, if you take out those tails, you get much smaller root mean squared errors in a Monte Carlo around the true parameter estimates by doing IIS than by doing any of the robust methods that we know of. Indeed, IIS is now recognized as being a robust method, and 2 years ago I gave a plenary on robust statistics at the International Congress on robust statistics, because IIS is catching on in that literature. And Johansson and Nielsen have shown that it's quite close to a Huber one-step skip estimator when applied in this context. So yeah, normality is essential for the program to make good decisions. And that's why we always do IIS and get rid of outliers. And then I don't think I've got a graph of the final distribution of the residuals, but they're very normal, and it passes a test for normality of the Yarkebere, Dornick-Nielsen type.
Thank you. I believe there are maybe 1 or 2 more questions downstairs, and I would encourage people at the top to get engaged.
In Oxford, downstairs are all invited. Upstairs are the riffraff. Now, that's not true here, but there's always a row because they cannot get microphones up to the upstairs. And I do strongly recommend if you are upstairs and you have a question, they can get microphones up here. It's not like we have to suffer at the Ashmole or Sheldonian. Yes. Next question.
Okay. I have used Autometrics for predicting air quality in Bogota. And at that time, I used daily data of air quality in several monitoring stations. And the predictions were okay. I used I combine forecast with different measures. But now I am interested in how to move from the daily data to the hourly data, especially to predict some air quality alerts, which sometimes you see if there is some emergency, or to send some message to populations to take some protective measures. So my question is, do you think if we move from daily data to hourly data, we lose some precision, or what other kind of measures can we use to improve the precision of the forecast? Okay, wonderful question, thank you. I was in Boulder last week giving a relatively similar talk, not quite the same, but similar. And they announced the outcome of the M4 forecasting competition. You're asked to forecast 100,000 time series and send in your forecasts up to 8 years ahead, 48 hours ahead, and so on. We were second in the hourly, daily, and weekly category, right, using our methods. So they do work right down to hourly. And the higher frequency, you've got to treat very carefully.
there's a diurnality begins to get very, very important, right? As we've discovered from, say, forecasting electricity demand, even minute by minute. It matters which minute and which day of the week and whether it's a holiday and whether it's raining. There's all sorts of things matter when you come down to hourly. But in general, you can check your model with the greatest of ease. Because many years ago, I proved a theorem that if you want to forecast at the highest frequency, but you're really interested in a lower frequency, then when you're modeling, say, the daily data, you should actually include all the hourly type measures, right? You should set it up in such a way you can do that. And if they matter, then it tells you you need to go to hourly. If they don't matter, then it tells you that what you really are interested in is the daily data. And this is done for GNP and inflation in the Eurozone, but it's very similar principles. So yeah, you can do it, but be very carefully. People recording hourly data, if it's done electronically, it's probably okay. If it's done by humans, and until recently, our Office of National Statistics sent out surveys to companies who wrote down what they thought, who sent it back to ONS, who then put it into a computer. And of course, sometimes it's just nonsense. Someone forgot a decimal digit or whatever. So you have to be terribly careful. If it's typed in even by the company, the secretary might be falling asleep late in the afternoon and more interested in watching a couple courting outside, and so she does 1 rather than 100. Yeah. IIS helps you in all of this. You should look at the data, but if you forgot to look at the data, it will pick out and take away the outliers that are due to data contamination.
Okay, I think there's a question at the top.
Yeah, I'm happy to contribute from the peanut gallery. Tom Rutherford, University of Wisconsin. Thank you very much for your fascinating talk. Those of us who work on climate, one dimension that we work on that was not addressed in your talk is basically adaptive response. And so I was curious as to whether work that IAS has been used for better forecasting climate extreme events. I saw a talk by Chris Funk from University of San Diego on forecasting using water temperature in the Central Pacific for forecasting sort of weather anomalies in Africa. And I'm just curious as to whether there's a literature that you've contributed to in that area.
Yeah, one of the other members of our group, Simeon Koopman in Amsterdam, has done this looking at the Southern Oscillation Index and whether or not it can give you warnings of temperature and rainfall, etc., well ahead. And that has now adopted IIS. Because even though it appears to deal with varying parameters, it doesn't actually, and the varying parameters can be quite complicated. So, yeah, all these things require you to think carefully about how to set up the problem, what is relevant in the study, keep all that, and then see if other things. I would actually expect step indicators to be more relevant in that, because if there really is a big uplift in the warmth of the Pacific off the Philippines, you can really worry for a long period ahead about how that's going to move across the whole ocean and hit Latin America and bring massive downpours, rivers in the sky, as I'd call them. Are any women going to ask questions around here? Come on, guys.
I think I've identified 3 people. So we'll
oh,
start
thank you. Right, one at least.
Let's start with Thomas, and then over here, and then we go here, and then we see if we've got any time left.
Thanks, David. Wonderful talk. I thought I'd give you an opportunity to explain a little bit about the temperature hiatus. If this meeting had been just a few years ago, you remember there was a dominance of the climate skeptics who were pointing to the fact that the whole community was talking about climate, but temperature wasn't actually going up. So you could, I think there was in the end an explanation with the water going into the deep oceans and stuff, but yeah. Maybe you could give a better explanation.
Well, it's again one of these things that there are probably a lot of influences. The absorption of heat deep down in the ocean to 2,000 meters was very much higher than people anticipated. The hiatus was also part of the Atlantic meridional overturn that was also happening at the same time. And there are these various forces out there. It was also probably a measurement error problem as well. There was some revision of the data that suggested it wasn't as big as people had thought. So I think all these influences mattered, and that's an argument for using very general models that's got everything that might matter in them, and then see what actually matters. And some of it came about because people claimed there was a hiatus. So they tried to fit a model which had something happening over the hiatus. That's not the way to do econometrics. Right? It's very hard to explain to people there's a bias there, a database bias. You've looked at the data, you've seen this, and oh, I will fit this and then claim a result. We look at the data, but we still include all the indicators everywhere. And if there isn't anything there, they won't pick it up. And if there is, you found that when you're analyzing coal prices with Samson, that putting it in didn't work, but using our methods, it did work. So thank you for your question, Thomas, and thank you for coming today despite your illness.
Okay, thank you to invite a question from a woman. Okay. Like many times we have a data that's really not continuous. It can be count, it can be censored. And the theories that you talk about here, that mostly you are applying to continuous data series. And many times you work with mortality, which is a count, and maybe like there, testing non-stationarity or all these things, it becomes very difficult. I also had a data set. I had 20,000 observations, but the data had a break. So for a few months I had the observation, and then for the rest of the months there was no observation. So in those cases, how carefully those things can be applied?
Yeah, there's a lovely paper by Neil Erickson from the Fed looking at rainfall in Mauritania. And that is the same problem. Many of the stations recorded 2 months a year or 4 months a year, but not the whole year. And he shows how you can use IIS to deal with all the missing data points, right? You can put in anything you like for them. Then if you put in IIS, it'll pick up all the ones where you put in rubbish. Right? So the actual rainfall deviated from the outturn on those periods. But also with hurricanes, I mean, it's very discrete data. It's not a continuous time series. It's all over the place. It's not even a cross-section in any useful sense. So, yeah, they can be adapted. It takes a bit of thought, but if you read Neil Erickson's paper, I can't remember his co-author, it's a jointly authored paper, then you'll see how they get round this problem for rainfall missing gaps in Mauritania.
Gib Metcalf. So I'm an economist, so I always tell my students there's no such thing as a free lunch, and so, though I think we'll have one after this. But so my question is, what's the downside? What's the cost of this technique, and where can we go woefully wrong with it?
Yeah, that's obviously a question that springs to many people's mind. Can there be free lunches in model selection? Well, I can tell you now, we have been utterly astonished at the number of free lunches we've come across once we've set the problem up this way. So, for example, to get exactly the same distributions of your theory parameter estimates as if you had fitted them and only them to data, but nevertheless selecting over 1,000 other variables, including indicators, outliers, etc., it's unaffected. It really is. It's easy to prove. Søren Johansen and I actually discovered it completely by accident trying to prove a different theorem. I actually discovered impulse indicator saturation completely by accident trying to study food demand in the US. And the participants in the competition had all started in 1952 because they couldn't explain Tobin's data from 1929. So I simply put in indicators for all the period between 29 and 52 to replicate what they'd done and discovered there were 3 massive, I mean massive outliers corresponding to a US food program in the middle of the Great Depression. If anything is going to affect the demand for food, it's a food program. You take out those 3 observations, they're 10, 12 standard deviations out from the rest of the data, the model fits the interwar period exactly the same way as it fits the post-war period, right? So I haven't come across serious costs. The only one I would mention is if you use too loose a significance level. It's what we call the house of cards problem. Say you've got 1,000 observations and use a 10% significance level. It isn't that on average you'll find 100, you'll often find 300. And the reason for that is you've found 100 spurious ones, which is overfitting. And that overfitting makes other ones look significant, which makes other ones look significant. And the way to determine it is you take away the least significant, and then the second least significant becomes insignificant. And this actually happened at a very embarrassing occasion in the Norges Bank, one of the neighbors here, where they were producing this fantastically complicated model of the Norwegian exchange rate vis-a-vis the dollar. And they had all sorts of things in there. And so I ran Econometrics and the same data, and it said, the Norwegian currency is a random walk. So they thought, oh, how could this possibly be? Look what we've got. So when I went to their model and took out the least significant variable, which had a t of 1, the next one had a t of 1, and then the next one, and everything collapsed right down until nothing was significant. So you have to use very tight significance levels, not pretend that something's significant, but you can still keep all your theory variables. They might have the wrong sign, they might be insignificant, it might show your theory's a load of nonsense, but it will be exactly what you would have got by fitting it to data. I think that's a pretty good definition of a free lunch.
Okay, thank you. We are running out of time, and I'm anxious that the gentleman over here gets to ask his question. If you can be very quick, please.
I was going to ask, and related to extending the time series, what happens when data changes to the data generating process?
Thank you. Wonderful question. We've done this for measures of sea temperature. In the past, they'd drop a wooden bucket over, haul it up, stop in a thermometer and record it. During the war, they couldn't do that, so they went down to the bilges and recorded it. Then after the war, they used a metal bucket, dropped it in and recorded it. Then they went on to more sensible methods of, you can deal with all of that. You can actually come through and show that there are changes in the measurement system and they matter. Also, James Duffy and I had a paper published recently in Econometrics Reviews showing that if you have strong trends and location shifts, you can even have data that are mismeasured by an integrated process and still get the right answer, right? Because the trends, just imagine a strong trend and your data does this. Well, the trend tells you it's wrong, right? So you can correct it. Imagine the data is going like this. It doesn't matter that your data is mismeasured. The big shifts will tell you the answer. So, yeah, thank you.
Okay, so we'll do the final question here.
Suppose that Donald Trump would have asked you, to what extent man is responsible for climate change? What would you answer?
Oh, virtually, totally. That's why I showed the CO2 graph. Almost all the increases in CO2 are anthropogenic. Most of the increases in CO2 translate into temperature increases in the planet with a delay, but there's also methane and changes in ozone matter as well. So it's almost all our behavior. But one of the interesting papers that's come out recently has shown in US states that have both a lot of solar and wind turbine energy used into the grid are driven out coal. Coal never beats the minimum of those two. In states with only one of them, it often is kept on. So the advice that you really need to get across to US states, that most states do accept that climate change is happening, get both. Then you'll have no coal generation. It's too expensive. Thank you.
Okay, thank you very much. So we close the session here.